final talk of the session is on SyCCL, which is a new CCL that exploits symmetry in collective communications. And the talk is given by Jiamin Gao, who is a researcher and staff engineer at Alibaba Cloud.
Okay. Hi, everyone. I'm Jiamin from Alibaba Cloud. Today, I'm going to share our work, SyCCL, exploiting symmetry for efficient collective communication scheduling. This is a joint work with Tsinghua University. Let's start from the big picture. Collective communication is the backbone of large-scale machine learning. Over the past few years, model sizes have exploded. Parameters just keep increasing. A model may experience multiple stages, such as pre-training, fine-tuning, and online inference. And each stage needs different communications. Under the hood, there are GPUs, NICs, switches, and different network architectures. In the middle sits the communication library. It bridges the raw hardware and the engine and models. Here's the catch. Collective performance depends a lot on the schedule. Take Nichols ring schedule as an example. Here are two servers, each with 8 GPUs. Inside the server, they connect by NV switch. Across servers, they use NICs. Nichols links all 16 GPUs into a long ring. Each data chunk starts at 1 GPU and goes hop by hop until everyone has it. For large data sizes, we want full bandwidth. But in the ring, for every 7 intra-server hops, there is only 1 inter-server hop. This means Nichols always used a fixed bandwidth ratio of 7:1 between intra-server and inter-server. However, real GPU clusters may be different. On our H800 clusters, the NVLink bandwidth is about 4 times NIC's bandwidth. So the ring schedule may waste bandwidth and is performance inefficient. In practice, we just replace 1 intra-server hop with 1 inter-server hop, and this can increase network bandwidth utilization and improve performance. And then for smaller data sizes, the latency dominates. In Nichols ring schedule, each data chunk must go hop by hop until everyone has it, so there are many dependent hops. So a better idea is to send to all GPUs simultaneously, and this can greatly reduce latency. So the problem is fixed schedules can be suboptimal because they waste bandwidth and increase latency. So what about handcrafting better schedules? Well, it's basically impossible because there are so many factors to be considered. First, the topologies are very different. There are different GPUs with different intra-host and inter-host connections. Second, there are different collective primitives, such as all-gather, reduce-scatter, and all-reduce, each with different communication patterns or demands. And third, the data sizes can range from tiny kilobytes to gigabytes, depending on the model and your deployment strategy. So put all that together, manual optimization just doesn't scale. Then let's try automation. Just generate schedules automatically. That sounds nice, but the search space is too large. First, there are many routing paths between 2 GPUs. In this example, sending from GPU 0 to GPU 5 has 2 choices. Go intro first and then inter, or inter first and then intro. Second, 1 chunk can be sliced into multiple pieces, and each piece can take a different path. And third, when 2 chunks go through the same link, either may go first. That is another branch. Because of these factors, state-of-the-art synthesizers like Taco and Tico just doesn't scale. They take hours or days to solve a schedule, and they still fail on large GPU clusters. This brings us to SyCCL, quickly synthesize near-optimal schedules. First, SyCCL models collective schedule synthesis as an MILP problem. And second, SyCCL exploits symmetry in the topology to reduce the search space and accelerate solving. Let me first show the MILP part. The key of MILP modeling is to represent all states and events as variables and encode everything into constraints. At the beginning, each GPU holds some chunks. The goal is for every GPU to receive their required chunks. For example, in OR-gather, each GPU should receive all chunks. We encode the topology into constraints, including latency and bandwidth parameters. The schedule is also encoded into constraints and is formalized like this: at some time, send some chunk over some link. We solve this with an MILP solver. The goal is to minimize the total time. Inside the MILP, we carefully model the transmission performance on links based on the latency and bandwidth parameters. First, the transfer time for a chunk over a link equals latency plus size. Sorry. Okay, let's go on. Okay, the transfer time for a chunk over a link equals latency plus size over bandwidth. A chunk must first finish its transmission over a link before it is sent by the received GPU. And second, the capacity for a link is determined by its bandwidth. If we send two chunks simultaneously over a link, both should slow down. This works, but the search space is too large. That's where symmetry helps. Next, I'll show how we use symmetry to reduce the search space and make the solving scale. The key insight is that GPU cluster topologies are highly symmetric. For example, in this topology, there are 16 GPUs on 4 servers. In each server, GPUs are connected via an NV switch. Across servers, GPUs are connected by network links. In this topology, there are 4 leaf switches. Each leaf switch connects 4 GPUs, with 1 GPU per switch. For example, the first leaf switch connects GPUs 0, 4, 8, and 12 on 4 servers. We can see that the topology is composed of multiple dimensions, such as the intra-host, the tier 1 inter-host. In each dimension, we can partition GPUs into multiple groups. The first dimension is for the intra-server connections. In this dimension, we can partition GPUs into 4 groups. Each group contains 4 GPUs belonging to the same server. The second dimension is for the tier 1 network links. In this dimension, GPUs are also partitioned into 4 groups. Each group contains 4 GPUs connected to the same leaf switch. In each dimension, all groups contain the same numbers of GPUs and the same link characteristics. They are identical. The groups are also isolated. That is, the GPUs in different groups can only reach each other through other dimensions, and only GPUs within the same group can reach each other in this dimension. Given these identical and isolated group characteristics, The communication across groups should also be consistent. Here is an example. In the intra-server dimension, if 3 groups, the group 0, 1, 2, use a ring schedule, then the last group 4 should also use a ring schedule. If we use the tree schedule, it should be suboptimal. To utilize this symmetry, we introduce Sketch, which defines per group demand. Existing synthesizers take the 4 communication demand as input and try to solve the 4 schedule directly, so the search space is too large. In fact, they allow the groups in the same dimension to have different schedules, though this will never be the result. In contrast, we first determine the per group communication demands. We call them sketch. The sketch restricts that the communication demands across groups in the same dimension to be identical, so that the solved schedules are also the same. With sketch, we can perform per dimension or per group problem solving using MILP. Compared to existing synthesizers, the problem scale is greatly reduced. Finally, we select the best overall schedule from the synthesized ones. This shows a sketch example. Given the input topology, primitive, and size, we first search the possible per dimension demand. Here, sketch 1 is an example. In dimension 0, all groups have the same demand. In dimension 1, only one group needs communication. Then we solve the communication demand for each group and generate the corresponding schedule. In this case, every group uses a ring schedule. There are more possible sketches, and each sketch leads to a different optimal schedule. And finally, we select the optimal schedule from all synthesized ones. Here's the full workflow. First, given the inputs, we search the sketches. We do symmetry-based pruning to reduce the sketch space to accelerate solving. And then for each sketch, we solve the demand and generate schedules for each group. Since there is a naturally speed and quality trade-off in MILP solving, so we use a hybrid solving strategy to keep solutions fast and near optimal. Finally, given the synthesized schedules, we run a high-fidelity simulator to estimate the performance of each schedule and select the best one. More details are in our paper, including the pruning rules, the solver settings, and the simulator design. We evaluate SyCCL on both real and simulated clusters, including a A100 testbed with 4 servers and a cloud fabric, and a simulated H800 cluster with 64 servers and a multi-rail networking. We test all gather, all reduce, and all to all, and compare SyCCL against NICO and TICO. On our A100 testbed, the 16 GPU all-gather performance for smaller data sizes, SyCCL outperformed NICO by up to 80% and had similar gains over TICO. For larger data sizes, the improvements are smaller but still clear. As for the synthesis time, SyCCL is 2 to 4 orders of magnitude faster than TICO. Let me wrap up. Collective communication is critical for large-scale machine learning. Fixed schedules are suboptimal, and current synthesizers don't scale. Our solution, SyCCL, combines MILP-based modeling with symmetry-based pruning. We see significant synthesis speed up and up to 1.3 times performance improvements. We have open sourced our code at GitHub, and welcome to use. Thank you. I'm happy to take questions.
Questions? In the back there?
Okay, thank you for your talks. Could you comment on the necessary of the automatic schedule synthesis whereas the expert crafted? And in practice, when does the synthesis method outperform the expert one?
You mean, can you repeat, please?
Okay. I want to ask about that. When does the synthesis method outperform the expert one?
Oh, you mean, is our synthesized schedules better than the manually written schedules?
Yes.
Oh, okay. I think the goal is for our synthesizer is to synthesize the optimal schedules for different inputs such as the topology and the collective and data size. And if you want, I think the biggest problem of manually writing schedules is that first, they require expertise to understand the topology and the hardware characteristics. And second, as the topology evolve and as new GPUs, new interconnection technologies involve, the input changes, and it takes time for people to write schedules manually. And if we have such a tool which can synthesize the optimal schedules automatically, I think this should be better than the human written schedules.
Okay, thank you.
Thank you for your great talk. And I have a quick question. As you have mentioned that it takes some time for SyCCL to synthesize the schedules. So how does SyCCL handle network dynamics like link failures or bandwidth fluctuations? Does it support update the schedule in real time or some other mechanism like incremental updates? Yeah, thank you.
You mean how SyCCL handles the dynamic networks?
Yeah.
Okay. I think this is a good question, and SyCCL actually SyCCL actually should first measure the network parameters such as latency and bandwidth, and then based on these measured parameters, we use an MLP model to solve the optimal schedule. And so if the network changes such as a link down or latency increase, the synthesized schedule may be suboptimal. But I think for such cases, a better solution is to perform some incremental synthesis or something else instead of a synthesizer from scratch. Yes, thank you.
Thanks for the talk. I'm Xiangyu from University of Washington. So I have a question about your symmetry-based space pruning. So will this introduce some suboptimality, or this is a pure gain? And whether you can include all constraints using your MILP-based synthesis? Thank you.
Yeah, thank you. When searching for sketches, we did do some pruning strategies to reduce the search space for sketch. In practice, in our paper, we also compare the results of using SyCCL without pruning and with pruning to prove that our pruning strategies does not lose the optimality of synthesized schedules.
Okay, thank you.
Great talk. I want to know how does SyCCL perform on symmetric or heterogeneous topologies? Can you synthesize quickly? And what is the fallback strategy?
You mean how SyCCL synthesizes schedules for asymmetric topologies? Okay, SyCCL is designed for symmetric topologies, and for asymmetric topologies, I think first they are not common in current GPU clusters, because for the consideration of whether training or inference efficiency, we should use the same GPUs with symmetric GPU clusters to train or inference. And if we use the asymmetric topology, I think the topology should still expose some symmetry characteristics in the topology. For example, if we have two types of GPUs, the first type should be put in the same network pod, and the other type of GPUs should put in another network pod. And in each pod, we should still utilize our symmetry insight to search the sketch and solve the schedule. And between different pods, maybe the search should be slow. And I think this will be our future work to handle such asymmetric topologies.
Yeah, thank you for the very lively. Oh, Mark, last question.
Okay, Mike Hanley. Oh, my voice is gone. If you switch between rings and rings and trees, you change the numerics. You change the order of the additions, and you get different. My voice is not working. I'll give up. I'll do it offline.
Great. Let's thank the speaker again. Mark will tell you the question offline because he was.
Thank you.